What you see here is we're starting with malonate ester. So you see that ester between the methyl. That's a malonate ester. And then we are creating carboxylic acid. Well, you may say that that is acetic acid, this is also substitution, so we can create substituted acetic acid. So this is a very traditional malonate ester synthesis. How this reaction done? Well, using the malonate ester is this proton is very acidic. I mean, this is a charge I want to recognize. This part will become that. And the other part, that's the one that goes away as a carbon dioxide through the decarboxylation step of the malonate ester after hydrolysis. So this proton is very acidic, so we can take it off by a base. You can use a variety of bases. Sodium hydroxide can be used, but I wouldn't use a sodium hydroxide. Why I wouldn't use sodium hydroxide? If you have an OH there, that will basically not only taking the protons off, that can be hydrolyzed in this ester. You don't want to hydrolyze yet. Because once you hydrolyze that, that becomes a carboxylate that could be nucleophile, that could react with oxygen. So we want to use a base that wouldn't be able to hydrolyze that. A dioxide can make an attack there, and then it will go up, comes back, kick that dioxide out. It looks like the same molecule. So that's the reason a dioxide is a choice here. Even though it go after the carbonyl of the ester, it looks like nothing happened. But if you're using a sodium hydroxide, you get this ester hydrolyzed. So that's why I suggest not to use a sodium hydroxide as a base, but to use a dioxide, same alkoxide that creating this ester would be good ideas. That can take the protons off almost 100% because that becomes very acidic by being between the two ester molecules. Now you make the enolate, malonate ester enolate. Then you need to find out what alkyl chain that you need to use. I mean, I highlight this portion so you can recognize this is the part that you need to add. It's not the whole thing from there, right? The alkyl chain you need to add is from up to that part. That is a isobutyl bromide or chloride. I mean, if you don't think this part's coming from this malonate ester, you may finding big alkyl chain, then you will end up making a wrong product. So you should be able to recognize a white alkyl halide for the reactions, being recognize which bond is getting created by these reactions. So this isobutyl bromide attacked by this enolate, same reaction we had talked about, it's just SN2 reactions. Once you have that, what you can do, you can hydrolyze this ester. Now you can use a sodium hydroxide. I prefer saponification because it's faster hydrolysis than heating up with acidic water. But you can simply use the heating up with acidic water to combine hydrolysis and decarboxylation together. But anyway, sodium hydroxide, if you're using it, that changes the ester into the carboxylic acid. But you know that will make these things, if you heat it up, you get CO2 goes out, and then you get the enol, but that will tautomerize into ketone forms, which becomes a carboxylic acid in the end. So you get the products. So this is basically how to use the malonic ester for the synthesis of the alpha substitute acetic acid. I just want to mention that you need to choose the white alkyl halide for the reaction, right? Because the species bond is getting made, not that one. But you can easily make a mistake of the bond using a wrong alkyl halide if you don't consider which bond is getting created by these reactions. So that is something that I want to use. But I just want to mention something else too. Some of you are wondering, why do we have to do this? If you want to make that, I mean, if I didn't specify the reaction needs to be starting from here, if I just say that if I want to make these things, some of you may think this way. Well, I will just use a enolate of the acid. Then that will make an attack to the alkyl halide, then I can make this one. it's kind of the same thing we've been talking about. Why can't we do this way? Well, first of all, things are not that simple. This thing is not going to work. That reason why these things are not going to work, you are making very basic carbon with the presence of a very acidic proton. So this proton becomes an issue. You cannot do that. In order to make an malonate there, you got to use a base. What the base will do first is to take these protons away and make an O- there, carboxylate. Then you can take these protons away. So if that happens, then you are making dianion. Dianion with two negative charges such a very close distance is going to be very bad for the molecule. You may see that this is two same charges, too much electrodensity going in this molecule. So that's why making this dianion is very challenging. I'm not saying that it's never going to be possible. It's very difficult. So that is not typically done. So instead, what you could do, you could use an ester. If you have an ester, then you can take these protons away. It's less acidic compared to ketosenaldehyde. But if you're using a strong base like an LDA, then you can make this proton goes away, make an malonate, that attacks an alkyl, then you can make the same molecule, obviously this is a ester or any other ester. So you have to hydrolyze it to make carboxylic acid. So if you want to make this one, that's the question. Then you don't have to start from here. You can start from ester, just acetate ester. Take these protons away by like LDA, then same alkyl halide that you'll be using there makes an attack. You get this substituted ester forms, hydrolyzed ester, and you get the carboxylic acid. You do the same thing. So then the question arises: why do you want to do this malonate ester synthesis and then making this thing going over like that using something very strange called the decarboxylation? What is the point of doing things that way? It looks like this step is a much shorter. This is a little bit longer step, this is a little bit shorter step. But why we go this way, not that way? The reason is, if you want to do this in a laboratory scale, it probably doesn't matter. But if you want to do this in a little bit bigger scale, you probably need to be concerned about the base that you use. In order to make this malonate there, that malonate, you've got to use a strong base, something like an LPA, which is a very, very strong base. Something that is needing extra portion, and then it could potentially give a problem, and then it is very expensive. Compared to that, if you're using a malonate, this using a very conventional base, sodium methoxide, some of you wondering where the sodium methoxide could come from. There is ethanol, it's a solvent, you just have to drop a sodium metal to it. It's very, very easy to prepare. And then this is a much, you can use a large quantity. It's a less basic compared to LDA, easy to handle, and then much cheaper. So the point of the malonate ester synthesis is always that using very common thing that you can find anywhere, and then make the reaction, it makes the same products that you could produce with the more expensive reagents that takes a more portions. So this has been using historically for the production of the molecule that you need in the industrial scale. So that is kind of a difference between why malonate ester acetosis synthesis still being taught, even though there's another way to do